All right, the topic for today is it's called contingency tables. And this is another way of getting probabilities in another format. So let me just explain a few things about the table that I have up here. I think the best way to start things is just with an example. So here, the study is to determine if stretching helps and prevents injury while exercising. So if you look, we have the stretchers. Of the stretchers, we have two things. We have those who stretched who were injured and those who stretched that were not injured. If you add 55 and the 295, that's 350. Similarly, in the do not stretch row, if you add 231 plus 219, that adds up to 450. And then this column here is just the column of injured. If you add 55 plus 231, it adds up to the 286. And the same with this column. When all is said and done, this thing here in this bottom corner not only is the sum of this column, it is also the sum of these rows, this row. So that's one way you can check to make sure the numbers are going to be acceptable, is that all that kind of stuff has to happen. Now, these kind of tables make it particularly useful for conditional probabilities. Let me show you some things we're going to do here. I know that they're putting a lot of words inside the parentheses, but I think I'm just going to do it this way. I'm going to call this by the letter S, this by the letter D, I, and N. So part A, what is the probability the athlete stretches before exercising? So what all they are asking us is, what is the probability of S? So the row of stretches totals up to 350 out of a total of 800. And I'll just leave it like that. There's no reason to put a decimal if I'm not going to do something with it. Next, what is the probability the athlete stretches given that no injury in the last year? So here, using my notation, this is what they are giving us to do. I have the probability that the athlete stretches, so it's going to be S bar, no injury is N. So the way you work these, this conditional probability, is you go to the N column, total is 514. That's like our sample space for this particular question. And then inside of here, just go to the block that talks about those who stretch. That would be 295 of them. I have some more questions than the book has. Just to become comfortable with this, my questions go like this. What is the probability, my first one I'm going to ask, that we had an injury given that they stretch? So what do? We go to the stretches and we look. The total number of stretchers is 350. Now, stay in that row for the total stretchers. How many of those were injured? Only 55. And I like, just to get extra practice, I'm going to probability of S/I, where I switch the letters. Now, however many people were injured is going to be my denominator. So let's take a look at those. Where's injured? So the number of people injured was only 286. How many of those injured were stretchers? 55. Notice in both these problems they have the same numerator. We did the probability of S/N. While I'm at it, let's do probability of N/S. So how many stretchers again did we have? 350. And of those stretchers, how many of those were not injured? 295. What would be the last one? We have I/N/D. We didn't get the D's in here, so we'll have does not stretch and injured. So how many injured people were there again? 286. Of those 286 injured, how many did not stretch? 231. Now, if I switch them, the probability of I/D, I already know this piece of information about them. It'll have the same numerator. Our denominator here then will be those who did not stretch, which is right there. That's a total of 450. All right, here's another problem illustrating these tables. I'm going to do just like I did before. I'm going to use letters for each of these things because you don't want to write these every single time. Female, male. So I think I got all the things I need. And let's see what it says here. It says, out of the males, what is the probability that the cyclist prefers a hilly path? So what you can do is, it says out of the males, so I can go, what's the probability that the person prefers a hilly path given that they're male? So let's take a look at the male row. That would be a total of 90. And how many of those males wanted a hilly path? 52 of them. Part B, are the events being male and preferring a hilly path independent events? So let's take a look here. There's a couple of ways we can do it. Let's do the probability of just H. So what's the probability of a hilly path? Well, that would be 90 out of 200. Now, I don't know if you can tell, these are not the same. So if I take a look, 52 over 90 is approximately, get a calculator here, so 0.57778. And 90 out of 200, I know what that is, equals 0.45. So these aren't the same. So since we have the probability of H/M does not equal the probability of just H, the events are not independent. Now, for practice, I'm going to make up my own problems for the rest of the problem. So let's start with this one. The probability of M/L. So let's scroll up. Let's see if L was a row or a column. L is a column. Total of 71 there. Of those 71, how many were male? That would be 26 of them. Let's turn it around. The probability of L/M. Remember, the numerator is going to be 26 on this, but I'll re-verify it just to make sure. M. How many males did we have? We have 90 males total. Of those males, how many liked the L? That would be 26 of them. Probability of F/L. Well, I already know that the L column had 71 people in it, so Of those 71, how many were female? 45. And then the probability of L/F, that's going to have 45 up there. And its denominator, how many females are in this table? The total number of females is 110. Probability of male/hill. Did we already do that one? I'm just looking at my notes and I'm not really paying attention. We did hill/male, so I'll do male/hill. How many people liked riding on the hills? 90. How many of those people were males? 52. I won't bother doing probability of H/M since I did that earlier. Let's try some with the females. Probability of female/hill. Well, based on this one up here, I already know the denominator is 90. And the probability of those 90 that prefer the hills, how many are female? Of those 90 who like it hilly, 38 female. Next, the probability of H/F. I remember that there's 110 females in this study. And we also know that the numerator is going to be the same as this one. Probability of M/W. Let's take a look at the W column. That is 39. That's the wooded path. Of those that like the wooded path, how many of those were male? 12. Probability of W/M is going to be 12 over how many? Well, I have to remember there was 90 males. And then finally, the last possible combo I think I can do, probability of female/wooded. Here, we know the denominator for the wooded is 39. Of those 39, how many were females? Actually, you know what? I can tell just from here, if I take 39 minus 12, the other has to be 27. But we'll go up to the table just to verify that. There it is, 27 for female in the wooded path. And the probability of W/F is going to be 27 divided by, and I happen to remember that there are 110 females in this problem. This is a slightly different table. Here you build up the probabilities. What we have is a mouse that has 3 doors from which to exit to try to go get cheese, perhaps. And the cat, of course, waits by the door. Or all 3 doors, actually. So it gives the probabilities after he's exited the door. However, this animal is choosing the doors at random. So what he does first is going to be 1/3. The door that he chooses, but it's at random. He's got an equal chance of doing each of those. To get the probability of what happens to this mouse, you have to take the 1/3, that would be, he's picked a door, and then multiply it by the probability associated with that door. That's where we have to go through this whole thing and take a look at it. So I want to circle some of the things we have here. 1/3 is going to be involved in all of our calculations. Right now I'm just circling all numbers. Some of these may not be useful to me. I'm just circling so I can see them easily. All right. we have, if he goes out the first door, the probability that he gets caught by Alyssa is 1/5. So he already has a 1/3 chance. Then you multiply it by the 1/5, and you end up with 1/15. Not caught is 4/5, so we're going to do 1/3 times 4/5. And remember, when you multiply fractions, you multiply across the numerators and you multiply across the denominators. So this is going to be 4/15. I don't think there's really any reason to go to decimals here. It might just make things a little messier. Unless they go about asking you more detailed questions, then you can convert later on. All right, if he goes out the second door, the probability he gets caught by Alyssa is 1/4. So remember, he has a 1/3 chance of the door he chooses. So 1/3 times 1/4 equals 1/12. And the probability is not caught is 3/4. So we have 1/3 times 3/4. Now you can write it as 3/12, or you could cancel these 3's and write it as 1/4. I'm going to leave it as 3/12. I think you're going to find having a fewer number of denominators is a good idea. Finally, let's take a look what happens with door 3, 1/2. That means the probability that she doesn't get caught is also 1/2. So we're going to have 1/3 times 1/2 will equal 1/6. And then it's the exact same thing for the other one. And as before, let's total these up. This is where it's nice to have the same denominators, because if they have the same denominators, all I have to do is add the numerators together. So in this first column, 1/15 plus 4/15 is 5/15. And the same goes here for the second column. Everything is over 12, so 1/12 plus 3/12 is 4/12. And finally, for the last one, we got 1/6 plus 1/6 gives us 2/6. Now, this other way is a pain, because if we decide to stick to these fractions, that means I will have to get a common denominator to add all these things together. I don't care what you put over here. If you want to put the decimals, you can. But as a reminder of common denominator getting, I will work this column up top, that's row up top, and this row in the bottom to remind you how to get a common denominator. What would work as a number that all three, 15, 12, and 6 would go into evenly? Well, it's too bad there's a 15 there, because if it was just 6 and 12, I would be in good shape, but I'm not. So I'm just going to do trial and error. If I double 15, I get 30. 12 does not go into 30, but 6 does, so that I'm getting somewhere. If I double 30 to 60, I notice that 12 goes into that, and 6 goes into that. So 60 will work as a common denominator. So the 1/15 is the same as 4/60. 1/12 is the same as 5/60. And finally, 1/6 is the same as 10/60. I'm going to do this a slightly second way to sort of remind you. One of the ways that you went to get a common denominator is you would factor all the numbers in sight. And then you would look at these numbers that are involved. You see I've got a 3, a 5. While there's a 2 there, if I use the 4, I'll be in business. What I'm saying is my least common denominator is going to be this. I'm going to choose the 3, A3, A5. But if I only choose 2, it's not going to be a big enough number. If I only choose 2, I'll only go up to 30. If I choose 4, I will go up to 60. So we end up, when I add these all up, just add along the numerators, I get 19 over 60. And as I mentioned, if you simply want to put a decimal over here, I have no problem with that whatsoever. In fact, I'll do that for the last one just to show you that I'm not lying when I say that. So in the last column, we started, I keep saying column where I mean row. We started with 4/15. So 4 divided by 15. I'll hit enter so it equals each time. And then I can see the rest of it. Then I'm going to add 3/12. So you can go plus. I just want to see 3 divided by 12. Enter. And then finally, the last one, so I want to do plus 1/6 plus 1 divided by 6. Enter. And I get 0.6833. Now, just out of curiosity, remember these are the totals. These are the totals of everything. That number plus this number should add up to 1. So all things should add up to 1 down here because that's all the probabilities. Let me take a look at that thing there. I'm going to, this number is on the calculator. I'm next going to add that to it to see if I get to 1. So I'm going to go plus 19 divided by 60. There it is. 1. Big fat 1. And so it's a short section. That's it for the tables.